Welcome to Mech Cosmos, Engineering Explained. At the start of every Formula One race, the cars accelerate from 0 to 100 kilometers per hour in under 2.5 seconds. They reach 300 kilometers per hour before the end of the first straight. They brake from 300 to 80 kilometers per hour in under 2 seconds, while the driver experiences forces of over 5G, pressing them forward into their harness. They corner at speeds that generate lateral forces of over 5G, pressing the driver sideways into the seat. And they do all of this for up to 2 hours, covering over 300 kilometers on a circuit that demands absolute precision at every single corner on every single lap. The Formula One car is the most technically advanced racing vehicle ever built. It is not just the fastest racing car. It is a machine that represents the absolute frontier of engineering in aerodynamics materials, science electronics, powertrain technology, and data analysis. Every component is designed to extract the maximum possible performance within the constraints of the regulations. Every gram of weight matters. Every thousandth of a second of lap time matters. And the engineering battle between the teams to find performance advantages is as intense and relentless as the racing itself. Teams spend hundreds of millions of dollars every year in the pursuit of fractions of a second per lap. Today we explain everything. How the engine produces over 1,000 horsepower from just 1.6 liters of displacement. How the hybrid system recovers and deploys energy with extraordinary precision. How the aerodynamics generate enough downforce to theoretically allow the car to drive on the ceiling. How the brakes stop the car from 300 kilometers per hour in under 100 meters. How the tires work at the absolute limit of adhesion. How the data systems process over 100 gigabytes of information every race weekend. And how all of these systems come together in a machine that pushes human and engineering performance to their absolute limits. We are Mech Cosmos, Engineering Explained. Let us begin. The engine of a modern Formula One car is officially called a power unit rather than simply an engine. This distinction is important because the power unit is not a single device, but a highly integrated combination of several energy conversion systems working together as one. The regulations that govern Formula One specify that all teams must use a 1.6-liter V6 turbocharged internal combustion engine combined with 2 motor generator units and an energy storage system. Understanding each of these components and how they interact is essential to understanding why the Formula One power unit is the most thermally efficient high-performance engine ever built. The internal combustion engine at the heart of the power unit is a masterpiece of precision engineering pushed to extraordinary extremes. It is a 1.6-liter V6 with a 90-degree angle between the 2 banks of 3 cylinders. Despite its small displacement, it revs to approximately 15,000 revolutions per minute, nearly 3 times the maximum RPM of a typical high-performance road car engine. At 15,000 RPM, the pistons are accelerating and decelerating at forces exceeding 8,000 times the force of gravity. The piston travels from bottom dead center to top dead center and back 250 times per second. The connecting rods experience tensile and compressive stresses that would destroy conventional steel components. Every internal component, the pistons, connecting rods, crankshaft valves, and camshafts, is made from exotic materials engineered specifically for this application. Titanium connecting rods offer the required strength at a fraction of the weight of steel. Ceramic-coated pistons withstand the extreme heat of combustion while remaining dimensionally stable. Nickel superalloy valves survive temperatures that would cause conventional steel valves to fail within minutes. The fuel injection system of an F1 engine operates at pressures of up to 500 bar, significantly higher than the 150 to 300 bar of a modern road car direct injection system. At these extreme pressures, the injectors atomize the fuel into an extraordinarily fine mist that vaporizes almost instantaneously when it contacts the hot compressed air in the cylinder. The precision of the injection system is remarkable. Each injection pulse is controlled to within microseconds and delivers an exact quantity of fuel measured in milligrams. The combustion process that results is so precisely controlled and so complete that the F1 engine achieves thermal efficiencies exceeding 50%. This means more than half of the chemical energy in the fuel is converted to useful mechanical work. For comparison, a typical road car petrol engine achieves around 35 to 40% thermal efficiency. The F1 engine achieves this remarkable efficiency figure despite operating at 15,000 RPM, an operating condition where most engines become less efficient due to increased friction and pumping losses at high speeds. The regulations limit the maximum fuel flow rate to 100 kilograms of fuel per hour at engine speeds above 10,100 RPM. This fuel flow limit is the primary constraint on the power output of the internal combustion engine component of the power unit. Teams cannot simply inject more fuel to gain more power. They are hard limited by the regulations. Every team therefore works to extract the absolute maximum power from 100 kilograms of fuel per hour through combustion chamber design, injection strategy, ignition timing, and exhaust system optimization. The turbocharger on the F1 power unit is one of the most sophisticated forced induction systems ever built. Unlike a conventional road car turbocharger, where the compressor and turbine are mounted on the same shaft and housed in the same unit, the F1 turbocharger uses a split architecture. The turbine, driven by exhaust gases from the engine, is located at the rear of the engine. The compressor, which pressurizes the intake air, is located at the front of the engine. They are connected by a shaft that runs through the valley of the V6 engine. This split architecture allows better packaging within the tight confines of the F1 car and improves thermal management by separating the extremely hot turbine from the compressor and intake system. The turbocharger is connected to the MGU-H, the motor generator unit heat, which is mounted on the turbocharger shaft. The MGU-H can operate in two modes. In generator mode, it extracts energy from the turbocharger shaft, energy that would otherwise be wasted as the turbine spins faster than needed, and converts it to electrical energy that is stored in the battery or used directly by the MGU-K. In motor mode, the MGU-H adds electrical energy to the turbocharger shaft, spinning the compressor faster than the exhaust turbine alone could drive it. This motor mode capability eliminates turbo lag entirely. When the driver demands sudden acceleration, the MGU-H instantly spins the compressor to operating speed, providing full boost pressure before the exhaust gases have had time to spool the turbine. The result is instantaneous throttle response with no lag, regardless of engine speed or load. The MGU-H is one of the most technically complex and expensive components in the entire power unit and represents one of the greatest areas of competitive differentiation between the engine suppliers. The MGU-K, motor generator unit kinetic, is connected directly to the crankshaft of the internal combustion engine. It is a powerful electric motor and generator combined in a single compact unit. As a motor, the MGU-K can add up to 120 kilowatts, approximately 160 horsepower, of additional power to the drive train. This electrical boost is deployed strategically by the team's software, typically during acceleration out of slow corners, where the additional torque has the greatest effect on lap time, or on long straights where the extra power increases top speed. As a generator, the MGU-K harvests kinetic energy during braking that would otherwise be dissipated as heat in the brakes. The harvested energy is stored in the energy store, the battery pack, for deployment later in the lap. The energy store is a lithium-ion battery pack designed specifically for the extreme demands of Formula One. It must be able to accept very high charging rates from the MGU-K during braking and deliver very high discharge rates to the MGU-K during acceleration deployment. The energy store capacity is limited by the regulations, and teams must manage its state of charge carefully throughout each lap to ensure energy is available when needed. The thermal management of the energy store is critical. Lithium-ion batteries lose performance and can be damaged if they overheat. A dedicated cooling system maintains the battery temperature within its optimal operating window throughout the race. The combined peak power output of the complete power unit, internal combustion engine plus MGU-K electrical boost, exceeds 1,000 horsepower from a package weighing approximately 150 kilograms. The power density of this unit is almost incomprehensible. A typical high-performance road car engine produces around 100 to 150 horsepower per litre of displacement. The F1 power unit produces over 625 horsepower per litre, more than 4 times the specific power output of even the most exotic road car engines. And it achieves this while simultaneously meeting fuel flow regulations and achieving over 50% thermal efficiency. The aerodynamics of a Formula One car are arguably more important to lap time than the power unit. A more powerful engine makes the car faster on the straights. Better aerodynamics make the car faster everywhere, on the straights by reducing drag, and on the corners by generating downforce that allows higher cornering speeds. The downforce generated by the aerodynamic devices presses the car toward the track surface, increasing the load on the tires and dramatically increasing the friction force available for cornering, braking, and acceleration. At racing speeds, a modern Formula One car generates downforce exceeding its own weight, meaning the tires are pressing on the track with a force greater than twice the car's actual weight. This is what allows the cars to corner at lateral accelerations exceeding 5G, forces that would cause a driver without training to lose consciousness. The front wing is the first aerodynamic device the incoming airflow encounters. It is a highly complex, multi-element structure with multiple individual wing profiles stacked closely together. The combined effect of these elements generates significant downforce at the front of the car, essential for front tire grip, while also carefully managing the direction and distribution of the airflow that will reach every other aerodynamic device further back on the car. The end plates of the front wing play a particularly important role in redirecting airflow around the front tires. The tires rotating at high speed create enormous turbulence, dirty air, that would severely disrupt the underbody airflow if it were allowed to flow inward. The front wing end plates direct the airflow outboard of the tires, keeping the underbody flow as clean and attached as possible. The rear wing generates downforce at the rear of the car, providing rear grip stability and traction under acceleration. Modern rear wings are relatively simple, two-element structures compared to the complex front wings. This simplicity is partly for aerodynamic efficiency, and partly because the rear wing incorporates the drag reduction system, DRS. When a pursuing car is within 1 second of the car ahead on designated DRS zones, the driver can press a button on the steering wheel that opens a flap in the upper element of the rear wing. Opening this flap dramatically reduces the angle of attack of the rear wing, cutting its downforce and, more importantly, its drag. The reduction in drag increases straight line speed by approximately 10 to 15 kilometers per hour, sufficient to allow the following car to close the gap and attempt an overtake. The DRS flap closes automatically when the driver brakes at the end of the straight. The underfloor is the most powerful aerodynamic device on the modern Formula One car and the area where the greatest development effort is currently focused. Since the reintroduction of ground effect regulations in 2022, the underfloor has generated the majority of the car's total downforce. The underfloor works on the venturi principle. The floor of the car is shaped to form two large tunnels, venturi channels, that run along either side of the car from front to rear. As airflow enters these tunnels, the tunnel cross-section narrows. By continuity, the air must accelerate as the tunnel narrows. By Bernoulli's principle, this acceleration is accompanied by a decrease in pressure. This low-pressure region beneath the car sucks the car towards the track surface, generating downforce. The crucial advantage of ground effect downforce over wing-generated downforce is efficiency. Ground effect generates large downforce forces with relatively little drag compared to conventional wings. It is also less sensitive to the turbulent wake from other cars, making the car more drivable when following closely and improving racing. The suspension of a Formula One car must satisfy seemingly contradictory requirements. It must be stiff enough to maintain the extremely precise relationship between the car's floor and the track surface that is essential for consistent aerodynamic performance. Even small changes in ride height can dramatically alter the ground effect. Yet it must also provide sufficient wheel movement to keep the tires in contact with the track over bumps and curbs. The stiffness of F1 suspension is extraordinary by road car standards. The car runs extremely low with minimal suspension travel. The springs and dampers are housed inboard within the bodywork. Pushrod and pullrod suspension geometries transmit the wheel loads to inboard mounted spring damper units through angled rods. This arrangement keeps the unsprung mass, the mass of components that move with the wheel, to a minimum, which improves the wheel's ability to follow the road surface rapidly and maintains tire contact. The brakes on a Formula One car are carbon ceramic disc brakes. This material choice is dictated by the extreme thermal demands of F1 braking. From 300 km per hour to 80 km per hour, in under 2 seconds, the braking system must absorb and dissipate an enormous amount of kinetic energy in a very short time. The temperature of the brake disc surface exceeds 1000 degrees Celsius during maximum braking events. At these temperatures, conventional cast iron brake discs used on road cars would simply fail. Carbon ceramic maintains its strength and friction coefficient at these extreme temperatures and dissipates heat rapidly. The glowing orange discs visible on F1 cars under heavy braking, sometimes visible even in daylight, are a direct result of the extreme temperatures involved. The brake discs on an F1 car are much thinner and lighter than road car discs. They are engineered for minimum weight and maximum heat capacity for the duration of a race, rather than for long service life. A set of brake discs may last only a single race weekend. The brake calipers are made from titanium or advanced aluminum alloys and are machined from solid billet to minimize weight, while maintaining the stiffness needed for precise brake pedal feel. The braking force distribution between front and rear axles, the brake bias, can be adjusted by the driver from the steering wheel during the race, allowing them to fine-tune the balance of the car under braking for different corners and as fuel load decreases throughout the race. The tires of a Formula One car are one of the most important and most strategically significant components of the entire vehicle. F1 tires look superficially similar to road car tires, but are fundamentally different in almost every aspect of their design behavior and purpose. F1 tires are designed to operate within a specific temperature window. For most compounds, the optimal tread temperature is between 80 and 120 degrees Celsius. Below this window, the tire is cold, and the rubber compound is too stiff to deform and grip the track surface effectively. The car slides and feels unresponsive. Above the window, the tire overheats. The rubber becomes too soft and begins to degrade, rapidly losing grip and wearing away quickly. Bringing the tires into their optimal temperature window and keeping them there is one of the most important aspects of F1 driving technique. Drivers use specific warming procedures, weaving on the formation lap, generating heat through lateral scrubbing, to bring cold tires up to temperature quickly. During the race, they must manage their driving style to avoid overheating the tires while still extracting maximum performance. Driving too aggressively causes the tires to overheat and degrade. Driving too conservatively allows them to cool below the optimal window, reducing grip. This constant management of tire temperature is one of the skills that distinguishes the best drivers from the rest. Pirelli supplies 5 different dry weather compounds for each season, ranging from the hardest C1 compound to the softest C5. Harder compounds have stiffer rubber that resists wear and degradation but provides less peak grip. Softer compounds have more compliant rubber that generates more grip by deforming more readily around the microtexture of the track surface, but degrades faster as a result. The regulations require each driver to use at least 2 different compounds during the race, creating a strategic element. Teams must decide which compounds to use, when to pit, and how to manage tire degradation throughout the race. A well-executed tire strategy can gain multiple positions without the car itself being faster than its competitors. The steering wheel of a Formula One car is unlike any other steering wheel ever made. It is a flat, roughly rectangular device that bears no visual resemblance to a road car steering wheel. It is covered in buttons, switches, rotary controls, and paddle shifters. It contains over 25 individual controls that the driver uses to adjust every aspect of the car's behavior while racing at speeds exceeding 300 kilometers per hour. The gear shift paddles behind the wheel change gear in milliseconds. Additional paddles operate the clutch for starts and pit lane maneuvers. Rotary switches adjust engine mapping, the power delivery characteristics of the power unit. Other controls adjust brake bias differential settings for the front and rear axles, energy deployment strategy, and radio communication. The driver must be able to operate all of these controls accurately while under physical G-forces, wearing gloves and traveling at racing speed. The layout of every control is carefully ergonomically optimized for this demanding operating environment. The data systems on a modern Formula One car generate and process a staggering amount of information. Over 300 individual sensors throughout the car monitor temperatures, pressures, forces, accelerations, speeds, positions, and system states continuously during every lap. The data acquisition system records all of this information at sampling rates of up to 1,000 times per second for critical channels. A portion of this data is transmitted in real time via telemetry to the team's engineers in the pit wall garage. The engineers monitor critical parameters, tire temperatures, brake temperatures, power unit performance, and aerodynamic loads in real time and communicate with the driver to advise on strategy and setup adjustments. After each session, the complete dataset, over 100 gigabytes per race weekend, is downloaded and analyzed in detail. The data analysis capabilities of the leading F1 teams employ hundreds of engineers and are comparable to those of the most sophisticated aerospace organizations in the world. The safety systems of a modern Formula One car are the product of decades of painful experience. The sport lost many drivers in its early decades to accidents that modern safety systems would have survived. The turning point came in 1994 when three-time world champion Ayrton Senna was killed at Imola, an event that shocked the world and galvanized the FIA into a comprehensive review of F1 safety. The survival cell, the carbon fiber monocoque that forms the central structure of the car surrounding the driver, must withstand impacts of enormous energy without significant deformation in the area surrounding the driver. The monocoque must pass a series of mandatory crash tests before it can be used in competition. The halo, the titanium arch that protects the driver's head, was introduced in 2018 after years of debate. It has already saved multiple drivers' lives in accidents where large debris or other cars have struck the driver's head area. The HANDS device prevents the driver's head and neck from being thrown violently forward in a frontal impact, protecting against the basilar skull fracture that killed several drivers in earlier eras. Mandatory head and neck restraints combined with the high-sided carbon fiber cockpit surround, and the halo have made Formula One dramatically safer while still providing the extreme performance that defines the sport. The Formula One car is not just a racing machine. It is a rolling laboratory that has contributed technologies to road cars that we now take for granted. Paddle shift gearboxes first appeared in Formula One in 1989 and are now standard on virtually every performance road car. Carbon ceramic brakes were developed for Formula One and are now available on high-performance road cars. Energy recovery systems pioneered in F1 are the direct ancestors of the hybrid systems in road cars today. Computational fluid dynamics simulation tools refined in F1 aerodynamics development are now used throughout the automotive and aerospace industries. The extreme demands of F1 competition drive technological innovation at a pace and intensity that no road car development program could justify, and the results of that innovation eventually find their way into the cars that ordinary people drive every day. That is how a Formula One car works. We are Mech Cosmos, engineering explained. If this video gave you a new appreciation for the most technically sophisticated racing machine ever built, Then subscribe, hit the notification bell, and join us for the next video, because every machine has a story, and we are here to tell it.